thanks to the Science Organizing Committee for this opportunity. It's a real pleasure for me and honor to give this talk. When I gave this title, it was a little bit ambitious title. I don't know whether I'll make justice for this. I'm not going to cover it, the entire, it's a very broad topic. I would cover some of the favorite aspects of this stellar archaeology with Monarchy as spectroscopic explorer and possibly some connection to TMT. So this is the cosmic timeline. Let's start from the beginning. So after the Big Bang, universe expanded and cooled, and there is age when the gas is cold and so universe started expanding. These are the dark ages. Then further, these gravitationally, these structures bound together to form what is called the mini halos, and the main cooling was molecular hydrogen that initiated the cooling and formed stars. We expect this first stars formed at these epochs. And further, these first stars, when if they are massive enough, certain ranges, they would explode as supernovae. And so once the supernovae explodes, they make a lot of heavy elements, and these heavy elements were the main ingredients that is expected to cool the gas and form the low mass stars, long-living low mass stars. So galaxy is defined by presence of long-lived low mass stars. So so first galaxies would have formed after the first stars, and then the present day. So what we are trying to do in the stellar archaeology is we observe the low mass stars, which are very old, and try to connect to the first supernovae with the chemical imprints of the first supernovae, whether it is present in the old stars of the Milky Way galaxy and the neighborhood, wherever you can resolve the stars in the Milky Way and the satellite galaxies. So that is the this thing about the stellar archaeology. Here again, illustrating the same thing what I said. So the first the mini halos, what we call the gravitationally bound dark matter system, is about 10⁶ solar masses. And you expect they could host some of the first stars. And when they explode as supernovae, and you would have low mass stars formed in this. So hierarchically, they form a big galaxy. And so this is just to give a time scale of various supernovae, various mass ranges, how it would contribute to the enrichment of the galaxy. So the massive stars like which explode as hypernovae, they have a very short turnaround time scale, and they need a lot of oxygen, magnesium, and iron peak elements. And the turnaround times are the 10⁶ to 10⁸ years. And then you have core collapse supernovae. These are the normal supernovae. They are slightly less massive than the hypernovae. They have a slightly longer time scale. And so the hypernovae, the main difference between the supernovae and the hypernovae is the zinc. Zinc is produced a lot in the hypernovae. And also hypernovae don't produce at least any of the neutron-rich elements. So that is one of the other proposal. But there are nowadays theories evolving. You could have jets to produce neutron captured elements and all. So then the type 1A supernovae, which is the wide warp and in a binary system, which would explode once the accreted mass after it becomes more than Chandrasekhar limit. So they produce most of the currently whatever see in the solar system or in our sun, the most of the iron peak element has come from the type 1A supernova. And so the AGBs, the asymptotic giant branch stars, contribute to carbon and nitrogen and S process, that is the slow neutron capture elements. So there are different time scale where different elements are enriched into the interstellar medium. So by studying the ratios of different elements, you can actually date the time scale of these events. So that is the basics about stellar archaeology. So this is the periodic table, just indicating various elements and the contribution from various. So hydrogen and helium are primarily the Big Bang nucleosynthesis, and rest of the elements are from various stars. So the key question of stellar archaeology is the overarching, the bigger goal is to understand the formation of galaxy and its substructure. Like a Milky Way has a disk, thin disk, thick disk, and it has globular clusters, it has a halo, and understand galaxy and its substructure and the stars within them, its chemical composition, starting from a hierarchical cosmological model. So that's a very, very big goal, but we are not nowhere close to that. But so because both in the theoretical modeling aspects, because it's very complex, you need to include so much of physics. So there are pre-processing methods people try to include in their cosmological model to get some of these features what we are expecting in stars. So that is the overarching bigger goal. And some of the key questions within the stellar archaeology, the topic of stellar archaeology is the nature of first stars in the universe and how the transition happened. Like we think theoretically the first stars are very massive, and now we see the most of the stars, if you look at the star Peter IMF, we see the solar mass is the one of the peak mass, like the low mass stars dominate the number. But how did this transition happen? Whether they just abruptly change from once the metal pollution started with the first supernovae, did it abruptly change, or there is a gradual progression mediated by, for example, reionization temperature of the universe would have kind of mediated this transition? We don't know. These are some things which people are interested in. And then the assembly history of Milky Way and the formation timescale of various substructure. And another important thing which we look at is the globular clusters, which we know it's like very old systems, but as part of the galaxy formation, when did they form in the galaxy? Did they form after the galaxy formation, or at which epoch? Did they peak during the epoch of reionization or during the actual peak of star formation? So we don't really know. So these are the major questions of this area. So how do we study the first stars? I would only address few questions in this. So how do we study the first stars? So as initially I said, like the metallicity keeps increasing in the galaxy. So the old stars expected to have very less metal. So the top three are the first stars would have zero metallicity. And so far we haven't detected any zero metallicity star, which is obvious because theoretically we think first stars are very massive. They would have exploded and gone. And maybe JWST should be able to detect. For example, JWST doesn't have a sensitivity to detect first supernovae. If it is a pair instability supernovae, which has a very highly, I think 10 power 53 or 54. Yeah.
Metallicity here is anything above carbon, right? Or
okay. Here I'm using, it's a little bit confusing. I'm using mostly iron as a metallicity indicator. There are some peculiar stars which has carbon but less iron. So we will come to that. Yeah. So, so JWST could, if there were first stars which exploded as a pair instability supernovae, we should be able to detect with JWST. So otherwise, the only way we can detect first stars is through this stellar archaeology. That is the only bet right now we have. And this is the metallicity distribution of this Briskin survey, which is the Canada-French Hawaii telescope, the survey from that. And so you can see they are very rare. They kind of really drop. And this is the recent from the guide. This is the distribution of metallicity. You can see the metal poor stars are low. I think this the lighter blue is primarily coming from a lot of contributions from the O-type stars and A and B O-type stars. They don't have any metals because they are too hard to have metallic transitions. Hydrogen and helium dominates. But they are very young stars. But we don't see the metallic lines, so the pipeline would put them into metal poor. So primarily this is the filtered. If you restrict the spectral type to be like above like F-type, they have put in a cutoff. I forgot about this. I think 6,500 or so. So then this is the metallicity. So you can see that they are very rare. And how do we normally search? It's a little bit basic for probably people should forgive me if it is too basic. So start with the low resolution spectra, and then you observe them at higher resolution. So this is an example of solar spectra. What you can see, so a lot of elements, like you can see the rich metallic lines. And this is the metal poor star, which is typical of our halo, minus 1.6. And this is minus 3.2 is 1,000 times metal poor than our sun. And this is, so you can see the scarcity of metallic lines in them. And this is the current record holder, that is minus 7.1, is the, it's more than 10 million times iron poor. But there is so far no iron line detected in the spectra, but the calcium is being detected. But you can notice that they are rich in carbon lines. You can see these molecular carbon bands. So even though it is minus 7.2, but the carbon is like just only 1,000 times metal poor compared to sun. But if iron is not even detectable, calcium is minus 7. That is how the upper limit is derived based on calcium abundance. We expect calcium to be similar to iron in normal supernovae, but it may not be the case in the exotic supernovae, which were in the first, during the early epochs. So one of the unexpected outcome of all these surveys was most of the iron poor stars are carbon rich. As you go to metal poor end, they're all found to be very carbon rich. So that is a kind of unexpected thing which people have not looked at it. And so this is the what we think is first stars probably make a lot of carbon. And so these are some of the plots showing this carbon and metallicity. Metallicity kind of, this is metal poor is earlier and metal rich is this is the kind of proxy to time. And so these are what you can see is the carbon rich stars are primarily in binary system. They are polluted by AGB companions. So they are not primordial. They have not formed from a carbon-rich material, but they were in a binary system where an AGB or asymptotic giant brown star made carbon and polluted the low mass companion, which we are currently seeing it. So they are carbon-rich, but not due to the primordial material. But these stars, group 3 and group 2, these are found to be carbon-rich. So these are not in binary system, and we think they are the direct descendants of this POP3 star are the first stars. And so we still don't know the progenitors. Still, it's an open question. Like people think possible theoretical proposals are faint supernovae. So basically, the supernovae didn't have enough energy to explode and throw away the heavy elements. So it only had enough energy to just outer layer, which is carbon and nitrogen-rich layers, were thrown out and fell back and formed a remnant. So only the polluted with the lighter elements. So that is one of the proposal for. So, but there are also other proposals like winds from a massive star. So these are possible proposals, but they are completely currently favored ones are faint supernovae because massive star winds would produce a lot of nitrogen. So another, so this is a favored thing, but this should be confirmed based on high redshift observations. High redshift supernovae should have these kind of faint supernovae dominating at higher redshift. That should be noticeable. And also the intergalactic medium abundances at high redshift should also show higher carbon abundances if this were real. So, but we don't reach that high redshift with the current observations. Maybe with JWST, we should be able to see some of the transients, maybe not the first transients, but at least with redshift, whether there is a trend that are fainter supernovae are similar to carbon-rich ones, or in metal poor system like dwarf galaxies, the supernovae which are in explode from a dwarf galaxies which are metal poor system, they should be having more of these faint supernovae. So these are the trends which are yet to come. But so then people also looked at carbon in a different galactic environment. Like for example, halo versus thick disk and bulge of the galaxy and global clusters. So what you can see is they are found everywhere. They are found even in the satellite galaxies, God satellites to Milky Way. They are found in, they are very metal poor system. They are thought to be the pristine galaxy. They are just the remnants of the hierarchical merging of the galaxy itself. So they have plenty of carbon enhanced metal poor stars. But we find the bulbs to be having much lesser carbon enhanced metal poor stars. So we still don't know. It's this is again a pristine survey, but we still don't have the sensitivity. So MSE would be really ideal to study because it has the infrared arm, which would be really good in probing these like highly extincted galactic towards the galactic center. So we should be able to study carbon enhanced metal poor stars. And another interesting thing is there are no carbon enhanced metal poor stars found in globular clusters. We think they are very old stars, but it's an old system, but there is none so far. So this would indicate the kind of environment and the epoch in which carbon enhanced progenitors of carbon enhanced metal poor stars should be formed. And again, this is indicating the galactic distribution of carbon enhanced metal poor stars. So they show that outer halo has more than compared to the inner halo. So then another thing which we also looked at it, looking at lithium, like for example, if carbon enhanced metal poor stars are progenitor, like formed from the polluted material of the first ejecta from the first supernovae, then they would have depleted lithium compared to a normal star at a similar metallicity. But what we find is they don't really, they have very similar carbon trend. And this is also done by another group, the Japanese group. They also found there is, but there is not much work done on the lithium abundance. This is a very faint line. So, and it's also in a case when the carbon is enhanced, it's difficult to identify these lithium features in a very cool star. So this similar trends in a normal and a carbon enhanced metal poor star indicates probably there was two parallel star formation modes which was happening in the early universe, so that they were mixed. And so this is something kind of very kind of a bold proposal, but I think this something which lithium would be helpful in identifying some of these progenitors and possible mixing process which is happening with the ISM. Another interesting aspect of stellar archaeology is production of very heavy elements in the very low mass stars. We know that AGBs, which the heavy elements are produced with slow neutron capture or a rapid neutron capture. Slow neutron capture process comes from the low mass AGB, that is 1 to 3 solar masses. And rapid neutron capture elements, we still don't know the sites, but we think neutron star mergers are the possible sites of rapid neutron capture elements. So, but we know the time scale. So based on the time scale, we expect only AGBs would contribute to the ISM, polluting the ISM at minus 1.8 or above. Similarly, neutron star mergers also contribute around minus 2. But we see plenty of stars which are enriched in these heavy elements at much lower metallicity. So we don't know yet how these elements are produced. So this is again just a slide to show the sites of our process. So this is the model. So what is the red points are the observations, and what you can see that this, and what this is the theoretical. You can see there shouldn't be any enhanced barium or europium rich star at the minus above metal poor than minus 2. But what we see is plenty of such objects. So that is, so we need a massive progenitor like. Though we have a direct evidence of our process production from the gravitational wave event like GW 0817, the kilonova had the light curve indicated the production of lambda in the ejecta, And also there is a detection of strontium in this spectra as well. So that gives a clear indication there is a neutron star mergers are the one of the sites. But in terms of galactic chemical evolution, we are unable to meet the timescale requirement. So that is one of the still open problem, which is people are looking at it. So another interesting thing is this is a ultra-faint dwarf galaxy, which is again very old. These are so there are two such dwarf galaxies. One is Reticulum 2 and another is Tucana 4, I think. So they are all the stars in that galaxy are enriched in our process elements. So our process sites, for example, what it should, based on archaeology, what we think is the site should make our process elements early on in the galaxy, and also they have to produce enough art process production so that it can pollute the entire dwarf galaxy, so that all the stars are reached. One episode of the event should make enough art process elements. And at the same time, there is also something called universality of art process. So this plot indicates this is what is the solid line is the solar art process. We know Sun has received contribution from various generations of supernovas. And so the art process pattern from the Sun and art process rich star, which is like 100 times greater than Sun, it has enhanced art process. So one event versus cumulative art process event. We see the pattern of the abundance and the main art process pattern is universal. It just hasn't changed. So there is something universal about it. Either it is driven by nuclear physics, not independent of it. Doesn't the art process, the way mechanism what produces art process doesn't depend on the astrophysical sites, but it's mostly driven by the nuclear physics. Or so this is something which, so any art process site should meet these conditions, like operate early in the galaxy, it should be rare and high yield event, and also it should adhere to the universality. So these are some of the constraints. So people have proposed many possibility, and so some of the recent papers which have come in. So there is a very like -3 metallicity art process event, which cannot be explained by neutron star mergers. People think it's a hypernovae, and they also find large zinc abundances, which should come from, again, a hypernovae could produce enough zinc. So this is again papers indicating that the galactic bulge has art process rich stars. So this is a very early phase, like a MSE would really, with a large aperture, it should be able to do a survey, and with a high resolution, it should be able to detect these art process rich events. And I also want to look at Pallavi's poster, like, so we have looked at the art process stars, progenitors do not produce magnesium. So that is also clear indication that it cannot be a core collapse, because core collapse supernovae produce magnesium also along with the European. So then the lighter art process elements like strontium, yttrium, and zirconium should be coming from more than one site, not the art process, the main art process site. It could also have additional site. So this is what we find from the differential abundances of art process rich stars, and we can encourage you to. And again, we're looking at the thorium abundances. Thorium, again, it's a radioactive element. You can do a cosmophotometry with that. And there are many more stars we know about which has thorium. And so you can see that how it is evolving with metallicity. So metal poor stars have lesser thorium, indicating that they have radioactively decayed to lead possibly. So we have a survey which is done at Witterhand glacial spectrograph, and some of this work has been done with that. And we also looked at some escapees from globular clusters based on the abundance trend. So these are all possible with a survey with this, which has a large volume, and you can, because you have to survey the entire halo and also detect some of these key elements like aluminum and sodium, magnesium. So these would need Aluminium is good you could do it in the infrared, and also in the blue, MSE spectrograph, the survey would go to, I think, 360 nanometers, so which is good for detecting aluminium. Yeah. Sorry. Yeah, so another problem, which is the puzzle of high europium in CNT stars. And again, this is the producing carbon-rich stars with highly europium is, there are a lot of theoretical models, and I think the people at IIA have done a lot of work on this. And yeah, I'll just quickly go to this, the connection between the MSE and our process. Our stellar archaeology. So in the era of MSE, like what we would have, what we need for a precision stellar archaeology is we need, so we have Gaia at this right now. So Gaia gives the 3D position, accurate position of stars, and also its motion. So we'll be able to understand the orbital motion of the stars, and also date their ages based on that. And with the LSST, when it comes, you can see the distances it covers, because large volume is like all these rare objects would become normal. Like, for example, you would see many of them that they could become, some of these rare objects could become normal objects when you have a large surveys. You would see, as we understand, as we get more and more spectra. So LSST would go to very large volumes. So we should be able to study the deep photometry would give accurate CMD, color magnitude diagram, and also variability. So these are all important for identifying transients, and as well as photometrically identifying dwarf satellites. And also Kepler missions like that, they also would give accurate stellar parameters using astroseismology. So this is the key specification. There is a MSE project talk, so I didn't dwell a lot on the MSE project itself. The Mauna Kea Spectroscopic Explorer had 3 modes, like low resolution and medium and the high resolution. So 40,000 high resolution is a kind of a unique survey, and no other survey has such a large spectral resolution, which is very important for detecting these heavier elements. And with Gaia, you can see this precision color magnitude diagram. So many small tracks, and these are all real stellar physics, which is making these overdensities. What you can see is some of these gaps. So what it is basically stars which are purely convective, transitioning to radiative envelopes. So these kind of small changes in the stellar physics can be probed with Gaia, and added to high resolution spectroscopy with MSE, we should be entering into the field of precision stellar genealogy, like I would say. So some of one way to also go beyond the modeling precision is the MSE would give a high resolution template for billions of stars. So we would be able to make empirical templates, because we are right now limited. Like, for example, I was looking at these odd even effects. For example, some of the stars, like if you're depending on the mass, you would make odd elements versus even elements different. It's a part of the nuclear process. Like you would, because alpha capture would dominate if you are massive star, and even elements would need like a weak interactions should happen. So even elements are high in the massive star ejecta versus odd element. So you can detect this odd even effect very clearly by going for differential abundances. Currently, we don't have the sensitivity, but if you use this kind of spectral empirical templates and differential abundance analysis, one should be able to reach this precision. And the connection with TMT and MSE is TMT has blue spectra. Like blue is where you have all the neutron capture elements have transition in the blue region. You can see all these elements, lithium, ruthenium, and all these hard process elements, and including uranium. So these are all key elements, and there are also isotopes you can probe. So this will give the hard process path of the progenitor. So So we're combining MSE class with a large survey of MSE and selecting stars for TMT would be a way forward. And TMT's blue sensitivity also is important for the oxygen because oxygen is a very key element, but we don't have a transitions. The OH molecules in the blue is the strongest one which you can detect at low metallicity. So oxygen is also, I wouldn't go into the beryllium part. So again, this is for example, if you want to search a pristine survivor of the first stars, top 3 stars, we should be looking at dwarf satellites. And with TMT, we should be able to go to the main sequence and we would have plenty of objects. As you go, current 8 to 10 meters only reach the RGD, and TMT should be able to reach the main sequence of the star, so of the galaxy. So you would be able to get spectra of 20 of them. This is my last slide. So with the Gaia, you would be able to see this overdensities of various structures, streams. These are streams, stellar streams, and which are detected based on this energy angular momentum diagram. So studying these chemical properties along with the kinematics would really tag us, like identify the birthplaces of individual stars in the galaxy. So, and these are some of the synergies which would be helpful for stellar archaeology. Thank you.
Long live India and France friendship.